This is silicon. Girl, no it's not. Okay, fair. This is just a block of clay. To make it easier for you to visualize, I labeled this one. This is silicon. Wait, Dia, so now we went from a block of clay to a lump of an element. And? Okay, hold the sass. But it's a good question. What is so special about that? I went from a nameless block of clay to a lump of the 14th element on the periodic table. But what could you really do with that? Well, what if I told you that with some changes, extra technology, you could turn this lump into things like my sister's laptop, my mom's headphones, the calculator I wouldn't pass math without, my sister's phone, the AirPods that I can't live without, the speaker that I'm going to use to play music while I edit this video on, the laptop I'm using to record this, the microphone that's recording me too. What if I told you that? Like this block of clay, silicon is pretty damn basic. But with some changes like doping, no, not the kind you're thinking about. I mean, making this seemingly perfect element imperfect. Silicon becomes the backbone of your technological life and the world.
So here's the deal. Silicon atoms are kind of like a Lego set. They have their own structure. But if you want to change how silicon behaves, you need to bring in some extra electrons that don't belong. That's where doping comes in. With N-type doping, we add an atom like phosphorus, which has an extra electron just chilling there, ready to join the fun. Now, the silicon's got a bunch of extra electrons. These bad boys are ready to move in and conduct electricity. But if you do P-type doping, we introduce something like boron, which has fewer electrons, creating a hole, basically an empty spot where an electron should be. These holes are just as important as the electrons because they create places for the electrons to jump into.
Alright, so now we've got our doped silicon. And when we bring together P-type and N-type silicon, you get a p-n junction. Think of it like two friends, one that's loaded and one that's broke. When they meet, there's an exchange that happens, but only under the right conditions. In this circuit here, I have a 2-terminal voltage source, a diode, which connects with wires to a 1K resistor. Notice how through the positive terminal that feeds into the anode of the diode, the circuit is completed and the current flows through. But if I switch the direction so the positive terminal fits into the cathode, the circuit stops there. Using a p-n junction, it controls the flow of electricity in the circuit like a traffic light. Okay, now let's switch gears. What if you want to make some decisions based on inputs? Welcome to the AND gate. Using 2 switches, you can see how the current flows in and then wants to go to the LED. Using these N-channel MOSFETs, if there's no current that flows to the gate, there is no connection between the drain and the source of the MOSFET. If I keep that channel open, the current stops with the drain of the top MOSFET. But if I close it and open the other one, it flows through and stops at the drain of the second one. They're both open, obviously there's no current. But if I shut them both, the current flows all the way through, goes to the ground, and the LED gets to be turned off. Here's an example with just the AND gate. Turn it off, no current. Turn the other one off, no current. Both on, current. But if they're both off, no current. Alright, so now you've got your p-n junction and your AND gate. But what if you could reprogram those logic gates and circuits however you wanted and whenever you wanted? That's where FPGAs come in. FPGAs are like the Swiss Army knives of electronics. Instead of having fixed, unchangeable logic, you can change the circuits to do whatever you want. You want to add more AND gates? Go for you. Need to do something super complex for AI? FPGAs got you. You just add some extra technology like flip-flops or other adders, and it all works out for you in the end. So to wrap it up, we started off with a boring lump of silicon, and we turned it into something super powerful just by adding dopants, those extra atoms or less atoms that change how silicon behaves in different technology. Then we looked at p-n junctions, the building block for connecting electricity and controlling it, and then we saw how AND gates help us make decisions with that electricity. Finally, we see how FPGAs let us design custom circuits on the fly, giving us a ton of flexibility to build whatever we want. All of this, it's what makes your phone, your laptop, your headphones, and so many other devices tick. Silicon may look like a basic material, but with the right changes, it powers pretty much everything we use. So there you have it, how we go from basic old silicon to creating the building blocks of tech and the world as we know it, our laptops, our phones, our headphones, just with a little bit of magic from PN junctions, logic gates, and FPGAs. Just using a little bit of science and a whole lot of imagination. If you like this video, make sure to stay tuned for my Medium article that follows my process on how I built these circuits, and my monthly newsletter that goes through my struggles and how I overcame them. And as always, stay sharp.